In this video, we're going to be talking about Newton's method, and Newton's method is a technique for approximating the zeros of a function. So we're talking about the places where a function crosses the x-intercept. Now, if you have a function that is factorable, like a polynomial that's factorable, or a trig function that you can solve set equal to 0, then this is pretty easy. But if you have a polynomial that's not factorable or not easily factorable, this might be a good method for you to use. And in fact, if you use any kind of graphing software or something like a TI-83 and you're trying to approximate zeros, it's probably going to be using some version of this method in order to approximate the zeros. So this gets used in a lot of approximation software. So basically what this uses are tangent lines. So this method uses tangent lines along with the intermediate value theorem, which we talked about in chapter 1, to approximate the graph of a function near its x-intercepts. So basically, you start with an initial guess, x of 1, and then you calculate the tangent line of the curve through that point, x of 1, f of x of 1. And then you use the intermediate value theorem to find another point in between, or another point on the graph that will be closer to the 0 line. And basically, you just kind of keep repeating this process until you get as close as you want to be. So notice we started with an x of 1, an x of 2, an x of 3, which is a little bit closer to the 0, and then if we did another round, we'd probably swing back this way a little bit, and eventually the method is going to land you pretty close to this value of c. So this is the method for approximating the zeros. If we let f of c equal 0, where f is differentiable on an open interval containing c, then to approximate c, we're going to use the following steps. We make an initial estimate x of 1 that's close to c. If you're looking at a graph, this is something that you can guess, just kind of eyeball the answer. If you're not, you could just pick something, but the closer you are to the actual answer, the less time it's going to take you to do this method. Then you would want to determine a new approximation using the following recursive formula. X of n plus 1 is equal to x of n minus f of x of n divided by f prime of x of n. So we're going to use this formula pretty heavily. This is something that you need to know. And the way this basically works is if you start with x of 1, x of 2, that would be the n plus 1, is going to be x of 1 minus f of x of 1 divided by f prime of x of 1. And if you plugged a 3 in here, you would have a 2 for all of these indices as well. Now, you're going to be given either a number of iterations that you want to complete, or you're going to be given an accuracy that you desire. So if it just tells you to calculate 3 iterations, you would do this process 3 times and your final answer would be your x of 4. If it asks you to get your answer to within a certain desired accuracy, then you're going to keep going until the difference between 2 iterations is less than, or the absolute value of it is less than whatever that accuracy is. So each time you apply this, it's called an iteration. Now, when you're calculating this, in general, for this class, you can round each step to 5 decimal places. Keep in mind, if a calculator is doing this or if a computer is doing this, it's going to use a lot more precision, but just for our purposes, we're going to go at least to 5 decimal places because most of our precision is not going to be beyond that. Now, if you're asked to do this with a precision that uses 10 decimal places, you would want to go out to at least 10 or 11 decimal places, but for our purposes, 5 is fine. So this one says calculate 3 iterations of Newton's method to approximate a 0 of f of x equals x squared minus 2, and we're going to use x of 1 equals 1 as the initial guess. Now I know you may be thinking, why would she do this? This is crazy. I could just set x squared minus 2 equal to 0. I'd get x squared equals 2. X would be plus or minus the square root of 2, which is about plus or minus 1.414, so on and so forth. Yes, but we're trying to prove the concept here, so that's why we're gonna use this method, because it's kind of a simple example. So we do need to know f prime of x in order to use this, and this is going to be 2x. Notice there are two zeros of this function x squared minus 2. There's a positive 1.414, so on and so forth, and a negative of that. And a lot of students wonder at first, okay, well, how do I know which of the zeros I'm going to get? And it's pretty simple, actually. Whichever one of your actual zeros that the number you use as your initial guess is closest to, that's the one that the property or that the formula is going to gravitate towards. So if you wanted to find an approximation of the negative, you would start maybe with -1 instead of +1. So whichever one you're starting closer to, that's the one that it's going to go towards. So it says 3 iterations, so we're going to start off with x of 1 equals 1. And for round 1, my first iteration, x of 2 is going to be x of 1 minus f of x of 1 divided by f prime of x of 1, which is 1 minus f of 1 divided by f prime of 1, which is 1 minus 1 squared minus 2 divided by 2 times 1, which is 1 minus -1 over 2, or 1.5. So that's my x of 1, that's my round 1. So for round 2, x of 3 is going to be x of 2 minus f of x of 2 divided by f prime of x of 2. So we're going to use the number that we got for round 1, that's 1.5, minus f of 1.5 divided by f prime of 1.5. Now from this point forward, if you don't want to show every single step along the way, as long as you show at least what you're plugging in, that's fine. I do need to see, the formula at some point and plugging into the formula. So basically either this or this. And it's also a good idea to at least kind of keep off to the side whatever the value of this fraction that you're subtracting is, because we're going to use that when we work the next type. So this is 1.5 minus 0.25 over 3 if you simplify, and that is rounded to 5 decimal places, 1.41667. So you can see that very quickly we've swung up towards the 1.5 and back down towards 1.41667. We're very close to this 1.414. So this tells us to go 3 iterations, so we're going to go one more round. And we'll end with x of 4, which will be x of 3 minus f of x of 3 divided by f prime of x of 3, which is 1.41667 minus f of 1.41667 divided by f prime of 1.41667. And just because these numbers are so long, I'm not going to rewrite this, but when I evaluate f at that divided by f prime at that, I get 0.00245, and when I subtract, I get 1.41422 when I round to 5 decimal places. So that would be my answer after 3 iterations, and you can see that is very close to the square root of 2. So that would be my answer after 3 iterations. So again, here's another example that asks us to do 3 iterations. So in this case, my f prime of x would be 3x squared, and I want my initial guess to be x of 1 equals 1.4. Okay, so for round 1, I would have x of 2 is going to be x of 1 minus f of x of 1 divided by f prime of x of 1. So that'll be 1.4 minus f of 1.4 divided by f prime of 1.4. So plugging this in, I get 1.4 minus -0.043537, going out to at least 5 decimal places. And when I say 1.4 minus that, I get about 1.44354, rounded to 5 decimal places. So for round 2, x of 3 will be x of 2 minus f of x of 2 divided by f prime of x of 2, or 1.44354 minus f of that divided by f prime of that. So that's going to be 1.44354 0.44354 minus 0.00129. So when I take my answer and subtract that, that's about 1.44225. And then 3 iterations means I need to go out to x sub 4. So that'll be x of 3 minus f of x of 3 divided by f prime of x of 3, which is 1.44225 minus f of 1.44225 divided by f prime of 1.44225. So that is 1.44225 minus 0.000004. That's the highest, or that's the number of digits you need to actually get something other than 0. So this actually comes out, when we just rounded 5 decimal places, 1.44225. So with the level of precision we're looking for, that's the answer we have. Now this problem is different for 2 reasons. Number 1, it says use Newton's method to approximate zeros of this long polynomial. Continue iterations until they differ by less than 0.0001. So instead of doing a certain number of iterations, we're going to keep going until we have the level of precision that we want. The other reason why this is different is because it doesn't give me an initial guess. It just gives me a graph. And if you're just given a graph, then you have to come up with your initial guess based on the graph. Now looking at this, I could choose something like -1, -1.5. I mean, I could choose anything. But that may not be the most efficient choice. I could pick something between the two, like -1.2 or -1.25, because the closer I get to the actual answer, the less iterations I may have to do. So a couple of things that we need to verify. I'm going to choose x of 1 equals -1.25, and I'm going to find my derivative, which is going to be 6x squared plus 2x minus 1. Now you could be given any combination of these problems. You may have a problem where you have to choose your initial guess and then do 2 iterations, or it may be where you're given the initial guess and you have to go with a certain level of precision. So just make sure you're reading the directions here. So x of 1 is -1.25. X of 2 is going to be x of 1 minus f of x of 1 divided by f prime of x of 1, which is -1.25 minus f of -1.25 divided by f prime of -1.25. which is going to be -1.25 minus, now when I do this fraction, I plug everything in, I get -0.01596. Now the reason why I told you to hold on to this number, we're going to take the absolute value of this. The absolute value of -0.01596 is equal to 0.01596, and this is greater than 0.0001. So that means we need to keep going. If that number is not less than the precision that you were asked to find in the beginning, then you're not done yet. So let's go ahead and get the answer here. This is -1.23404. So I definitely need to go again. So x of 3 will be x of 2 minus f of x of 2 divided by f prime of x of 2, which is going to be -1.23404 minus f of -1.23404 divided by f prime of -1.23404. So when I plug in this fraction, I'm going to get -0.00029, and that's what I'm going to compare. So since the absolute value of -0.00029 is still greater than 0.0001, then I need to keep going again. So this is going to be -1.23375. So we got to go one more. X of 4 will be x of 3 minus f of x of 3 divided by f prime x of 3, which will be -1.23375 minus f evaluated at that, divided by f prime evaluated at that. And when I evaluate this fraction, I get negative 0.0000009. Let me check that. Yes, that is 7 zeros. So since the absolute value of this piece right here is definitely less than 0.0001, then that means that we are done. And to 5 decimal places, my answer is negative 1.23375. So that would be the answer within the amount of precision that they wanted me to find. So we'll do one more of these. In this case, it says, again, continue iterations until they differ by less than 0.0001, but they do give us an initial guess of x of 1 equals 2. So f prime of x would be negative 1 plus cosine of x, just to prove that you can do this with trig functions without any problem. X of 1 is 2. X of 2 is going to be 2 minus f of 2 divided by f prime of 2, which will be 2 minus negative, or sorry, we're going to have 1 minus 2 plus sine of 2 divided by negative 1 plus cosine of 2. So when I plug that into the calculator, I get 0.06405. And again, that is definitely an absolute value greater than our precision that we want. So this is about 1.93595. X of 3 would be 1.93595 minus f of that divided by f prime of that, which that fraction evaluates to be 0.00139, so that's a lot smaller, but it's still too large. So that's about 1.93456. And we do x of 4. My fraction evaluates to negative 0.0000005. So that is definitely within the realm of precision that we want, and when I add these and round to 5 decimal places, or subtract a minus, and round to 5 decimal places, I get 1.93456. So that ends up being my final answer. So this is Newton's method.